Imagine walking into a room where Albert Einstein himself is sitting quietly, smoking his pipe, lost in thought. The room is filled with the giants of physics, men who rewrote the laws of nature. Now imagine a young, fast, talking, enthusiastic physicist from New York stepping in with a stack of papers, a few scribbles, and a mind full of wild ideas. That was Richard Feynman, 27 years old, about to present to Einstein. At that time, physics was in turmoil. Quantum mechanics worked beautifully for small things like atoms and electrons. Relativity worked perfectly for big things like planets and galaxies. But these two worlds didn't speak the same language. Somewhere between them, truth was split. And Feynman was one of the few who wanted to build a bridge. He was working on a problem that had haunted physicists for decades. How do particles like electrons interact with light and with each other at the quantum level? The math was messy, infinitely messy. When scientists tried to calculate, the answers blew up to infinity. Nothing made sense. So Feynman did something different. Instead of trying to tame the math, he reimagined the process. He started to see particles not as tiny billiard balls moving through space, but as events, as probabilities, as all possible paths that a particle could take, all happening at once. He called it the sum over histories. He realized that an electron doesn't take one path from point A to point B. It takes every path. Straight lines, loops, zigzags, impossible detours, all of them. And somehow, when you add up all these possibilities, the paths interfere with one another like ripples on a pond, canceling out the impossible ones and leaving behind the reality we observe. That idea, that nature explores every possible route, and yet gives us a single outcome, was revolutionary. It wasn't just new math, it was a new way to see reality. When Feynman presented this to the Princeton audience, Einstein was there. The older physicist, whose own work had bent the universe, listened quietly as Feynman described his strange world, a world where particles don't follow definite paths, where reality itself seems to decide only when you look. Einstein had long struggled with the weirdness of quantum mechanics. He believed the universe was orderly, predictable. God does not play dice, he once said. But Feynman wasn't trying to argue with Einstein. He wasn't defending quantum uncertainty, he was describing it as it is, without judgment. And when he finished, Einstein smiled. Not a full endorsement, but respect. Because Feynman had done something rare. He had looked at the same problem Einstein had pondered and seen it with fresh eyes. Feynman's approach eventually became quantum electrodynamics, QED, one of the most precise and successful theories in all of science. It describes how light and matter interact with astonishing accuracy. Every time your phone screen lights up or a laser scans a barcode, QED is at work. But let's pause. What does this actually mean? If every electron takes every possible path, what is reality really? Is there a real path at all? Or is reality just the interference pattern of all possibilities, the residue of everything that could have been? Feynman himself once said, "I think I can safely say that nobody understands quantum mechanics." And he meant it. Because understanding here isn't about solving equations. It's about accepting a world that refuses to fit our intuition. We humans evolved to see definite things. A ball thrown through the air follows one path. A stone dropped into water makes a single splash. But the quantum world laughs at that simplicity. It shows us that what we call the path, or the event, is just one of many possible realities, filtered by probability, by observation, by the limits of our measurement. And here's where the struggle begins. We want to know. We crave certainty. We want to say, the particle went this way, but the universe seems to whisper, no, it went every way. Einstein resisted that whisper. Feynman embraced it, and that difference is profound. Because to embrace uncertainty is to see the universe not as a clockwork machine, but as a grand symphony, where every note, every possibility plays a role in creating the harmony we observe. Feynman's sum over histories suggests that the universe doesn't choose a single path until it must, that the very act of existing involves exploring the impossible, maybe what we call reality. is just the final interference pattern of all those infinite possibilities. And if that's true, then every moment, every decision, every movement isn't a single event, but a tapestry woven from what could have been and what is. Think about it. Every photon of light reaching your eyes has explored every possible route through space, every possible interaction, before arriving precisely where you are now. We are made from the same fabric, a cloud of probabilities, collapsing into form only when the universe demands it. So when Feynman presented to Einstein, it wasn't just a young physicist showing his math. It was one explorer showing another that the map of reality was far stranger and more beautiful than anyone had dared to imagine. And in that moment, that quiet, respectful exchange between two of the greatest minds, something shifted. Physics didn't become simpler, it became deeper. Because what Feynman really taught us wasn't how to calculate, but how to see. To see that uncertainty is not ignorance, but nature's most honest expression. That simplicity is not always truth, and that behind every equation there is mystery, not to be solved, but to be understood. Perhaps the most profound lesson Feynman left us with is this: the universe does not owe us understanding. It only offers us wonder, and to be curious, endlessly, joyfully curious, is the most human thing we can be. Reality, after all, is not what we think it is. It is everything that could be, choosing, moment by moment, to become what is. The air in the Princeton lecture hall was quiet that morning, almost heavy with thought. At the front of the room sat Albert Einstein, his pipe resting between his fingers, his eyes half closed, as if he were listening to something deeper than sound itself. Around him, scattered across the wooden seats, were the most brilliant physicists of the century, men who had bent the laws of nature and rewritten reality itself. The year was somewhere in the mid-1940s, and physics was standing at a crossroads. Through the tall wooden doors walked a young man from New York, thin, energetic, a little disheveled, and very much alive. Richard Feynman was only in his 20s, yet there was something in his presence that made people stop and listen. He spoke quickly, laughed often, and questioned everything. But on this day even he felt the weight of the room. To stand before Einstein was to stand before a legend, a mind that had redefined time, space, and gravity. And Feynman was there to talk about something that not even Einstein had managed to untangle: the strange, unpredictable world of quantum mechanics. He carried no grand presentation, no polished performance, just a few papers, some chalk, and an idea so peculiar that even he wasn't sure if it made sense yet. But Feynman's way was never to pretend certainty. He didn't speak to impress. He spoke to understand. The other scientists, Oppenheimer, Pauli, Dirac, were used to elegance and structure. Feynman, in contrast, approached physics like a street musician approached melody, by feel, by intuition, by sheer curiosity. As he began to write on the blackboard, the chalk squeaked. He drew lines, arrows, and loops that didn't look like the usual equations of classical physics. He wasn't just solving. He was telling a story about electrons, photons, and the invisible dance that connected them. His voice carried a kind of rhythm, rising and falling with the logic of discovery. The problem he was addressing had haunted physicists for years. It was simple to describe, but nearly impossible to solve. How does light interact with matter? When an electron emits or absorbs a photon, what exactly happens? The equations that describe this process, known as quantum electrodynamics, worked beautifully in small cases, but as soon as you tried to calculate real interactions, the answers went wild. The math exploded into infinities, numbers that didn't make physical sense. Einstein, sitting there, had once struggled with similar questions. He had shown that light could behave like particles, tiny quanta of energy, and yet he couldn't accept that nature itself might be fundamentally random. For him, the universe was logical, continuous, governed by laws that could, in principle, be known. But the younger generation, the quantum generation, was saying something far stranger, that on the smallest scales, reality behaves like a game of chance. Feynman was different from both sides. He wasn't fighting for or against randomness. He was trying to see how nature actually worked beyond philosophy and preference. He once said that he didn't care if something was ugly or confusing as long as it was true. And that spirit defined him in that lecture room. He started to describe something that no one had quite said in that way before. He suggested that maybe the reason the equations were giving infinite answers was because we were thinking about particles the wrong way. We kept asking, which path does the electron take? But what if that was the wrong question entirely? Feynman proposed that the electron doesn't take a single path at all. It takes every possible path from point A to point B, every curve, every detour, every imaginable route through space and time. You can't say which one it really takes, because reality itself doesn't decide until it absolutely has to. To the audience, this sounded absurd. How could a particle be in all places at once? How could nature allow that? But the beauty of Feynman's idea was that it wasn't mere imagination. When you calculated the probability of a particle arriving somewhere by adding up all the possible paths, every crazy, looping, twisted route, the numbers worked perfectly. The infinities disappeared. As Feynman sketched on the board, Einstein leaned forward slightly, not to challenge, but to listen. It wasn't often that he found someone who could surprise him anymore. Here was a young physicist who didn't hide behind equations or dogma. He was trying to see nature directly, even if it meant letting go of everything that felt comfortable. And that was perhaps the moment when respect quietly passed between them. Einstein didn't agree with everything Feynman said. He couldn't. The idea that particles explore every possible history went against his deepest instincts. But he recognized honesty in Feynman's reasoning, a rare humility before the mystery of nature. After the talk ended, there was a silence, the kind that follows when something meaningful has been said, even if no one can yet explain why. Einstein smiled faintly. Feynman later recalled that moment not as a triumph, but as a quiet acknowledgement, a signal that he had spoken the language of truth, even if it was strange. That day wasn't just about a young scientist impressing an elder genius. It was about a meeting between two different ways of seeing the universe, one that sought order and determinism, and another that accepted uncertainty as a natural part of existence. In that small lecture room, surrounded by chalk dust and cigarette smoke, the conversation between certainty and curiosity continued, a conversation that still defines physics today. Feynman didn't claim to have solved the puzzle. He only offered a new way to look at it. And maybe that's what earned Einstein's respect. Not the solution, but the courage to admit that the universe might be stranger than anyone, even Einstein, had imagined. Physics in the early 20th century was like a house built with two sets of blueprints. Each one worked beautifully on its own, but they didn't fit together. On one side stood Einstein's theory of relativity, smooth, continuous, elegant, describing how space and time bend, how gravity curves the universe itself. On the other side stood quantum mechanics, strange, jittery, unpredictable, describing the behavior of atoms and subatomic particles. Both were true, both passed every experiment, but the two refused to speak the same language. Somewhere in the fabric of reality, a seam had torn. When physicists tried to bridge that seam, they ran into chaos. They wanted to understand how light and matter interact, how an electron emits a photon, or how two charged particles affect each other. The theory that was supposed to handle this was called quantum electrodynamics, or QED. It was meant to unify electricity, magnetism, and light at the smallest scales. The rules were known. The math seemed straightforward. But when the calculations were done, the answers were nonsense. A simple problem like how two electrons repel each other, something we could easily describe in classical physics, gave quantum physicists nightmares. Every attempt to calculate the force between them led to numbers that blew up to infinity. You could try to fix one equation, but another would break. It was as if nature itself refused to give a clean answer. For most scientists, infinity in an equation meant failure. Physics is supposed to describe measurable, finite things. You can't say that the energy of a particle is infinite. That's not a description. It's an admission of ignorance. And yet every path they took led back to the same mathematical abyss. Einstein, in his quiet skepticism, saw this as a symptom of a deeper problem. He had always believed that quantum mechanics, though useful, was incomplete. To him, the universe was rational at its core. There must be hidden variables, hidden causes, that explained the apparent randomness. He couldn't accept that the universe rolled dice. Nature, he said, must have rules elegant, continuous, and knowable. But the younger generation, Heisenberg, Schrödinger, Dirac, had grown comfortable with uncertainty. They had seen that the quantum world does not follow the tidy paths of planets or pendulums. Instead, it moves in probabilities, wave functions, and sudden jumps. You can't say where an electron is, only where it might be found. You can't say when it will emit a photon, only the odds that it will. Feynman grew up in this new world, but he didn't fit entirely within it. He didn't like abstract philosophy, nor did he worship mathematical beauty. What mattered to him was whether something described nature as it is. He didn't care if it sounded strange or unorthodox, as long as it worked and made sense deep down. So when he looked at the infinities of quantum electrodynamics, he didn't see disaster. He saw a sign that our picture of reality was incomplete, not the reality itself, but the way we were describing it. Maybe the equations weren't wrong, he thought. Maybe the assumptions behind them were. Maybe we were asking the wrong question. Physicists were trying to picture an electron as a point moving through space, interacting with photons along the way, like billiard balls colliding on a table. But what if that image itself was flawed? What if particles weren't tiny marbles at all? What if they were events, happenings spread over space and time, linked by probabilities rather than paths? The problem was not just mathematical, it was conceptual. When you calculate how an electron moves from one place to another, you usually assume it takes a single, definite path, like a baseball flying through the air. But the quantum world never confirmed that assumption. Experiments like the double slit showed the opposite. Particles behave like waves, interfering with themselves as if they traveled every possible route at once. This was the contradiction at the heart of physics. On one hand, experiments worked only if you treated electrons as waves of probability. On the other hand, measurements always showed discrete particles, one spot on the detector, one event in time. The theory had to explain both. And the more physicists tried to reconcile them, the deeper they fell into confusion. It wasn't that no one had tried to fix the infinities. Great minds like Dirac, Pauli, and Heisenberg had spent years on it. They came up with renormalization, a way to cancel out infinities by redefining certain quantities like mass and charge. It worked in practice, giving accurate predictions. But to many physicists, including Einstein, it felt like cheating. It was like sweeping infinity under the rug just to keep the numbers tidy. When Feynman arrived on the scene, he saw that everyone was fighting the math. They were patching equations, adjusting constants, arguing over interpretations. But almost no one was questioning the picture of what was happening underneath. Feynman's genius was not that he invented new math, but that he reimagined the story behind the math. He started to think, what if an electron doesn't take one path between 2 points, but all of them? What if nature itself doesn't choose until the very end? In that case, all those infinite possibilities would interact, some adding together, others canceling out. The infinities might not be mistakes. They might be part of the process, a sign that every possible history is contributing to what we finally observe. That idea sounded almost mystical, but it wasn't philosophy, it was physics. It would later become the sum over histories, a method that allowed Feynman to calculate results cleanly where others found only chaos. But at that moment in history, all this was still forming in his mind. The world of physics was waiting for someone bold enough to say, maybe the problem isn't the answers, it's the way we're asking the questions. The struggle over infinities wasn't just technical, it was psychological. Physicists had spent their lives believing that nature must be rational, that equations must yield finite, clean results. Yet the universe was whispering something else, that the truth might be far stranger and far less comfortable than anyone wanted to admit. In that tension between the old certainty and the new mystery stood Feynman, ready to look at the chaos and say, "Let's start over." Richard Feynman had a habit of looking at problems differently from everyone else. When others saw walls of complex mathematics, he saw patterns, shapes, and stories hidden beneath the numbers. He wasn't satisfied with elegant equations that nobody truly understood. He wanted to see what nature was doing. That was his gift, to look past the formalism and imagine what was actually happening in the invisible world of particles. At the time, most physicists were trying to fix quantum electrodynamics by tinkering with the existing equations. They would adjust constants, add corrections, and hope the infinities would cancel out. The approach worked sometimes, but nobody could explain why it worked. It was as if the universe was giving the right answers for the wrong reasons. Feynman found that deeply unsatisfying. He once said, "I don't like that. I don't like things that don't make sense." He believed the heart of the problem wasn't in the numbers, but in the picture of reality those numbers described. Everyone was thinking in classical terms, imagining particles as tiny billiard balls zipping through space, bouncing off one another, exchanging photons like little messengers of energy. But this mental picture came from everyday experience, not from the strange truth of the quantum world. Feynman began to suspect that this classical imagery was holding everyone back. He started from scratch. He imagined an electron traveling from one point to another. In classical physics, it takes the single path that minimizes action, the straightest, most efficient route, like a beam of light following the shortest line through space. But experiments had already shown that particles don't behave this way. In the double-slit experiment, for instance, a single electron somehow interferes with itself as if it had gone through both slits at once. That made no sense if the electron was a little ball following one trajectory. So Feynman asked himself a radical question: what if, instead of taking one path, the electron takes every possible path, every curve, every zigzag, every loop, every improbable journey from point A to point B? Some paths would be short and smooth, others wildly indirect, even looping backward in time. What if nature explores them all simultaneously? At first, this sounded absurd, even to Feynman. But then he did what he always did when confronted with something unbelievable. He tested the logic. If an electron could indeed take all possible paths, then each path would contribute something to the final outcome. You could assign to each path a number, a kind of weight, depending on how likely it was. Then you could add up all these contributions to find the total probability of the electron being detected at some point. The amazing thing was that when you did this mathematically, everything fit. The impossible infinities disappeared. The probabilities worked out perfectly. The behavior of particles matched experiments with astonishing accuracy. Nature seemed to act as though it really did explore every possible route, not metaphorically, but literally as a fundamental rule of existence. Feynman realized that the universe doesn't choose a single path. It considers all of them, and through the interference of these possibilities, reality emerges. When two paths reinforce each other, the outcome becomes more probable. When they cancel out, the outcome disappears. In this view, what we see as a definite event, an electron landing on a screen, a photon bouncing off a mirror, is not the result of one path being taken, but of countless paths overlapping and interfering until only one visible pattern remains. This was the birth of what would later be called the path integral formulation of quantum mechanics. But to Feynman, it wasn't just a tool, it was a way to think. He often drew little diagrams to represent these interactions, now famous as Feynman diagrams. Each line and vertex told a story of particles interacting, exchanging energy, and influencing one another. What had once been abstract equations became a kind of visual language, intuitive and alive. Feynman wasn't trying to make the theory prettier. He was trying to make it real. He wanted to imagine the universe as it is, not as human intuition expects it to be. He once explained that nature doesn't make a distinction between what we call possible and impossible. Every possibility counts. It's only through the interference of all possibilities that the familiar world appears. This way of thinking opened a door. Instead of trying to force the quantum world into classical patterns, Feynman let it be strange. He stopped trying to make it look like the macroscopic world we understand. He accepted that the universe might work according to rules that are far beyond our everyday logic. And once he accepted that, the beauty of it emerged. The path integral wasn't just a mathematical trick. It was a deep statement about reality, that every event in the universe is a sum of everything that could have happened. Every outcome is shaped not by one history, but by all histories. The world we experience is the interference pattern of infinite possibilities. When Feynman looked at the equations that came out of this method, he knew something extraordinary had happened. The results were cleaner, simpler, and more accurate than any previous formulation. The theory predicted experimental results with unbelievable precision. But more than that, it made sense. It had a story, a picture, a logic. It was the kind of breakthrough that comes not from working harder, but from seeing differently. While others had been trying to fix the cracks in the wall, Feynman had rebuilt the foundation. He had found a way to let nature speak its own language instead of forcing it to speak ours. In doing so, he showed that understanding doesn't always come from control. Sometimes it comes from humility, from letting the universe tell us what it is, rather than insisting on what we think it should be. Imagine tossing a ball through the air. You watch it rise in a graceful arc and fall smoothly back into your hand. In our everyday world, that's how motion works. A single path, predictable and clean. If you were to draw it, you'd trace one perfect curve. But the quantum world laughs at that simplicity. Down there, at the scale of atoms and electrons, nature doesn't take one path. It takes all possible paths at once. Feynman's great insight was that a particle, like an electron, doesn't choose the shortest route between 2 points the way a ball does. Instead, it simultaneously explores every possible route, straight lines, wiggly ones, long detours, even backward loops in time. In the quantum realm, every path that can exist does exist, at least for a moment. Nature doesn't commit early, it keeps every option open. To understand this, imagine 1,000 tiny invisible travelers, leaving the same starting point, each taking a different path to the same destination. Some take the short route, others spiral and loop. When they all arrive, they interact, their effects overlap, like ripples meeting on the surface of a pond. Some ripples reinforce each other, creating a bright spot of high probability. Others cancel out, leaving quiet zones where the chance of finding the particle is almost zero. The result of all this interference is the pattern we actually observe. This picture, though strange, captures what experiments had already shown. In the famous double-slit experiment, electrons fired one at a time through 2 narrow openings form an interference pattern on a screen, as if each electron were a wave interfering with itself. When you try to detect which slit the electron actually passes through, the interference disappears. It behaves like a particle again. Feynman's formulation explained this beautifully. The electron really does take both slits and every other imaginable route in between. But when we observe, when we force the question of which path, the superposition of possibilities collapses into one. The interference vanishes, and the illusion of a single history emerges. Feynman called this way of describing motion the sum over histories. Each path contributes a little piece to the total probability of what we see. The universe, in effect, performs an enormous calculation, adding up all possible ways something could happen. The final outcome, the path we actually observe, is the sum of all those contributions interfering together. He turned this vision into a mathematical method, the path integral. You start by assigning a number to each possible path, a kind of phase representing how that path contributes to the final result. Then you add up all the phases, every single one, even the wildly improbable paths. The impossible ones cancel each other out. The most likely ones reinforce. Out of this cosmic averaging, reality emerges. This approach didn't just make the math work. It explained why the math worked. It showed that the smooth, deterministic world we see at large scales is just the result of countless quantum possibilities blending together. The chaos of the micro world becomes the order of the macro world through interference. What makes Feynman's view so striking is that it forces us to rethink what happens even means. In classical physics, an event has a clear story. A particle goes from here to there, following a single trajectory. In Feynman's universe, there is no single story until the very end. Every story happens, and only through their interference does one emerge as the version we call real. This way of thinking is unsettling because it denies our deepest intuition. We like to believe that reality is definite, that something either happens or it doesn't. But in the quantum world, existence is not about certainty, it's about contribution. Every possibility plays a role, even the ones that never manifest. Reality is not a line, it's a superposition of lines, all interacting. Feynman often explained this with humor and simplicity. He would say that an electron behaves like a mischievous traveler who refuses to take the straight road. It insists on exploring every possible detour. When you measure where it ends up, you're seeing the result of all its adventures interfering with one another. You're not seeing the path it took, because it didn't take one, it took them all. The beauty of this approach is that it connects the unpredictable quantum world with the predictable world we experience. For big objects, like a thrown ball, the many possible paths almost all cancel out, except for the one closest to the classical path of least action. That's why balls, planets, and cars behave predictably. The quantum strangeness is still there, but it averages away. Only in the microscopic world do the other paths make themselves known. Through the sum over histories, Feynman gave physics a new language, one that didn't just calculate probabilities, but describe reality as a grand interference of possibilities. The equations that emerged from this method became some of the most precise ever tested. Quantum electrodynamics could now predict, to more than 10 decimal places, the magnetic moment of the electron and the scattering of light from charged particles. No other theory in science has achieved such accuracy, yet despite its success, the idea remains deeply mysterious. It doesn't tell us why the universe behaves this way, only that it does. It describes a world that is inherently participatory, a world where everything that could happen contributes to what does happen. In this view, existence itself is not about certainty, but about the sum of possibilities collapsing into form. When Feynman spoke of his discovery, he never pretended to understand why nature worked this way. He simply said, "It works. That's all I can tell you." And maybe that was the truest thing of all, that behind the perfect precision of physics lies a universe that refuses to give up all its secrets, no matter how deeply we look. When Feynman finally presented his ideas to the great minds of his time, the room was heavy with both skepticism and curiosity. These were not ordinary scientists. Sitting there were legends, men who had shaped the foundations of modern physics, men whose words had become the language of the universe itself. And among them, quietly observing from his seat, was Albert Einstein. The moment was historic, though no one could have realized it then. It was more than a scientific discussion. It was a meeting between two different ways of seeing reality. Feynman stood at the front, chalk in hand, eyes bright, his hands moving as if he were sketching thought itself into the air. He didn't speak like the others. He wasn't formal, nor did he hide behind abstract mathematics. He talked in pictures, in stories, in little thought experiments that made invisible ideas feel tangible. He spoke of electrons traveling along every possible path, of nature exploring all possibilities and somehow giving us only one outcome. The older physicists listened, intrigued but cautious. The young man's ideas were bold, even reckless by the standards of that time. Einstein watched silently. He had always been a man who valued clarity, reason, and order. His entire worldview was built on the belief that nature obeys precise laws. Even when he developed relativity, a theory that shattered classical physics, he never abandoned the idea that the universe must be consistent and deterministic at its core. For him, randomness was a sign of incomplete understanding, not a fundamental feature of reality. When quantum mechanics began to take shape in the 1920s, Einstein admired its success but disliked its philosophy. He once said, "God does not play dice with the universe." Feynman's presentation was the complete opposite of that certainty. It described a world in which every particle behaves like a gambler, exploring all possible moves, adding them up, and letting interference decide the result. There was no single path, no hidden variable guiding the process. The universe, according to Feynman, was fundamentally probabilistic. It didn't decide until it had to. To many in the room, this sounded like a direct challenge to Einstein's view of the cosmos. But Feynman wasn't trying to provoke. He wasn't defending chance or rebelling against order. He was simply describing what the equations and experiments revealed. Nature, as far as he could see, didn't care about human preferences for certainty. It just behaved this way. The strange truth wasn't something to be tamed. It was something to be understood. What made Feynman different from most physicists was that he didn't argue philosophy. He argued reality. He didn't say the universe should behave like this. He showed that it does. His diagrams, his equations, his reasoning, they all led to predictions that matched experiments better than any other method. The math worked, and the results were stunningly precise. Einstein, for all his reluctance to accept quantum indeterminacy, respected results. He could recognize genuine insight when he saw it. He listened carefully, occasionally smiling as Feynman animatedly explained how particles seem to borrow energy for tiny moments or interfere with themselves. Feynman spoke with the excitement of someone not claiming to have solved everything, but to have found a new way of looking at the puzzle. When Feynman finished, there was a silence, the kind that falls when something unexpected has just touched everyone in the room. No applause, no debate, just thought. Then Einstein slowly, almost imperceptibly, nodded. It wasn't an endorsement of Feynman's entire worldview, but it was a gesture of genuine respect. For a man who had built his life around the idea that the universe was logical, it took humility to acknowledge the clarity in someone who was describing it as inherently uncertain. Einstein and Feynman were very different kinds of thinkers. Einstein had built an empire of logic and geometry. Feynman was the explorer who wandered into the unknown with intuition as his compass. Einstein wanted the universe to be a grand equation, perfectly ordered and comprehensible. Feynman accepted it as a wild landscape of probabilities, governed by laws that were precise yet unpredictable in their outcomes. The beauty of that encounter wasn't in agreement, but in understanding. Feynman didn't try to defeat Einstein's vision, he expanded it. He showed that uncertainty didn't mean chaos, and probability didn't mean ignorance. In his hands, randomness became a structure, a pattern, a rhythm through which nature expressed itself. He had taken Einstein's deterministic canvas and painted over it with a kind of shimmering complexity that still obeyed rules, just rules of a different kind. It was a quiet revolution. What Einstein had done for space and time, Feynman was now doing for quantum reality. He was showing that beneath the appearance of order lies a deeper kind of order, one made not of certainty, but of possibility. The universe wasn't playing dice after all. It was performing an infinite sum of possibilities, and what we call chance was simply the interference pattern that emerged. After that day, Feynman's approach spread quickly. His diagrams became the universal language of particle physics. His way of thinking transformed not only how scientists calculated, but how they imagined the quantum world. Yet even as he rose to fame, Feynman always spoke of that meeting with humility. He didn't boast that he had impressed Einstein, he only said that he had been understood. And in the world of physics, being understood by Einstein was no small thing. That moment was not about victory. It was about connection, the passing of respect from one generation of genius to the next. Einstein represented the search for absolute truth. Feynman represented the acceptance of mystery as truth. In that silent exchange between them, physics grew up a little more, embracing the idea that knowing the universe doesn't always mean making it simple. Sometimes it means learning to live with its strangeness and loving it for exactly what it is. Feynman's strange new way of describing reality, which at first seemed like a bold thought experiment, soon became something much more. It evolved into the most accurate and successful physical theory in human history. Quantum electrodynamics, QED, was no longer an incomplete mess filled with infinities and contradictions. It became a masterpiece of precision, a bridge between mathematics and reality so exact that its predictions could be tested to 10 decimal places. No other scientific theory, not even Einstein's relativity, had ever reached that level of perfection. QD explained how light and matter interact. Every spark, every reflection, every glow of color in the world is an electron exchanging photons, little packets of light. Feynman's diagrams gave scientists a clear way to picture these events. Each line represented a particle's path through space-time, and each intersection showed where particles met and exchanged energy. By combining all possible diagrams, physicists could calculate the total probability of an interaction happening. It was like turning the invisible chaos of the quantum world into a language of pictures. But beyond its technical success, QD raised profound questions about the nature of reality itself. If every electron takes every possible path, what does that say about existence? Is there even such a thing as a single, definite history? When we see a photon bounce off a mirror, we imagine it traveled in a straight line, reflecting at one angle. But according to Feynman's theory, that photon actually explored every possible angle, every possible bounce, even paths that looped and twisted before returning to our eyes. We only see the one that survives the interference, the one path that remains after all the others cancel out. To most people, this sounds impossible, but experiments proved it true. Nature doesn't commit to one history until it has to. Until the moment of observation, reality remains a kind of cloud, a collection of overlapping possibilities. Every path exists in potential, waiting to be resolved. This isn't philosophy, it's physics. When measured, the predictions match exactly what the quantum equations demand. Feynman himself admitted that he didn't really understand quantum mechanics in the traditional sense. He famously said, "I think I can safely say that nobody understands quantum mechanics." What he meant was that the theory works flawlessly, but it defies ordinary logic. We can calculate what happens, but we can't fully grasp why it happens that way. The quantum world follows rules that our human brains weren't built to comprehend. At the heart of QED lies an uncomfortable truth. Reality doesn't behave as a sequence of definite events. Instead, it's built from probabilities. A particle isn't at one place or another. It's described by a wave function, a mathematical expression that represents all possible states. When we measure it, that wave function collapses, and one outcome becomes real. But before that, all outcomes coexist. This means that what we call reality is not a single story unfolding, but a vast web of potential stories, constantly overlapping and interfering. Feynman's formulation captures this beautifully. It doesn't say that particles choose paths. It says they all contribute. The universe, in its simplest events, performs a kind of grand computation, summing over every possibility and letting the mathematics decide what remains. The world we see is the interference pattern of all those hidden paths. This view of reality is deeply humbling. It suggests that certainty is an illusion created by scale. When billions of particles interfere, their probabilities smooth out into the predictable patterns we recognize as classical physics. Large objects, planets, trees, people, appear solid and deterministic not because they are fundamentally different, but because their quantum uncertainties cancel out. The randomness remains, but it hides beneath the surface, averaging itself into stability. In that sense, what we call normal reality is simply quantum weirdness made invisible by numbers. The laws that govern the universe are the same at every scale. It's just that at our level, the interference is so overwhelming that we see only one outcome. The ball thrown through the air seems to follow one path, because the countless other quantum paths it could have taken cancel each other out almost perfectly. This perspective forces us to rethink the meaning of knowledge. If every event is built from countless possibilities, then what we observe is not the only version that could have existed. The universe might not be a fixed story, but a continuous act of selection, a narrowing down of infinite potential into the specific moment we call now. Feynman didn't find that frightening. He found it beautiful. For him, uncertainty was not ignorance. It was the signature of nature's creativity. He once said that the joy of science lies not in certainty, but in the ability to live comfortably with doubt. That's what set him apart. Where others sought ultimate explanations, Feynman sought deeper questions. QD showed humanity something profound. The universe does not need to be simple to be comprehensible. It can be vast, tangled, and strange, and still obey precise mathematical rules. The quantum world may be unpredictable in detail, but its overall structure is perfectly lawful. Order emerges not from the absence of chaos, but from the way chaos interferes with itself. Through Feynman's eyes, reality is not a clockwork machine, but a living sea of possibilities. Every atom, every flicker of light, every heartbeat is the result of uncountable paths combining to make the single world we experience. The universe is not built from certainty, it's built from wonder that somehow works with impossible precision. When you begin to see the universe the way Feynman did, something fundamental changes in the way reality feels. You stop seeing the world as a fixed, solid stage where events happen one after another, and start seeing it as a dynamic ocean of possibilities, a sea of all that could happen, interacting to create what does happen. It is a shift so deep that it doesn't just alter how we think about physics, it changes how we think about existence itself. Feynman's path integral idea implied something extraordinary, that the universe does not decide on a single history until it must. Everything that could happen contributes, even if only for a moment, to the final outcome. Every photon of light that reaches your eyes, every electron in your body, every atom that makes up the air you breathe, all of them are shaped by a process of cosmic interference. Reality, in this view, is not a chain of causes and effects, but the sum of infinite possibilities canceling and reinforcing one another until one version remains. This isn't just a mathematical curiosity. It means that every moment of your life, every piece of matter and energy around you, is the final product of countless unrealized histories. The light bouncing off the page in front of you has traveled not one straight path, but all possible routes through space. The atoms that form your body have been part of an unbroken chain of probabilities stretching back to the birth of the universe. What you see and feel is the residue of everything that might have been, filtered through the strange arithmetic of nature. Feynman's genius was to show that this bizarre picture isn't just an interpretation, it's measurable. When scientists used his methods to calculate physical interactions, the results matched experiments with breathtaking accuracy. The theory that described this, quantum electrodynamics, could predict the behavior of particles to a degree of precision unmatched by any other branch of science. That level of accuracy tells us something profound. The universe really does behave this way. The weirdness isn't in our imagination, it's woven into the fabric of being. And yet this understanding brings with it a kind of humility. For all the power of QED, it doesn't explain why nature chooses to behave like this. The math works perfectly, but it gives no reason for its own truth. We can describe the how of the universe with astonishing clarity, but the why remains silent. Feynman accepted this silence. He never pretended that science would solve every mystery. Instead, he believed that the beauty of science was precisely in that tension, in living with uncertainty and still finding joy in the discovery. He often compared understanding the universe to appreciating a flower. You can study the physics of light, the chemistry of color, the biology of petals, and still see that it's beautiful. Knowing the mechanisms doesn't take away the wonder, it deepens it. The more you learn about how the universe works, the more impossible it seems that it could exist at all, and yet it does, effortlessly, continuously. The philosophical weight of Feynman's ideas is enormous. They suggest that determinism, the comforting belief that everything follows a fixed script, may be only an illusion that emerges from large numbers. Beneath the surface, the universe is restless, exploring countless alternatives in every instant. Our everyday sense of cause and effect, of before and after, is just the large-scale shadow of something far stranger and more fluid. And what does that mean for us, the observers within it? It means that observation itself is not a passive act. In the quantum world, to observe is to participate. The interference of possibilities collapses into one outcome the moment it interacts with the world, and that includes us. We are part of the process that gives shape to reality. The universe doesn't exist as a finished picture waiting to be seen. It is continuously being painted, stroke by stroke, by the interaction of all things with one another. Feynman never claimed that this meant consciousness creates reality. He was too honest for that kind of speculation. But he did show that observation, the act of interaction, is woven into the laws of physics. To see something is to change it. To measure it is to define it. The world is not separate from us. We are participants in its unfolding. That is perhaps the deepest philosophical lesson in Feynman's work. That knowledge doesn't separate us from the universe, it unites us with it. The scientist observing a particle, the poet watching the stars, the child catching a reflection of sunlight on water, all are part of the same cosmic process of exploration. Every observation is a small piece of the universe becoming aware of itself. And when you think about that, something in the human spirit resonates. The equations, the experiments, the theories, they are not just technical achievements. They are expressions of our need to understand where we are and what we are made of. Feynman's physics, stripped of all its complexity, says something profoundly simple, that reality is not a thing, but a process, not a static world, but a living conversation between possibility and realization. If you look at the world through this lens, even ordinary things take on a new light. The flicker of a candle, the shimmer of sunlight on water, the pattern of stars in the night sky. All of it is the outcome of countless invisible events, every photon and atom taking part in an endless quantum dialogue. The universe isn't happening somewhere out there. It's happening here, in every moment, in every breath. Feynman's gift was to remind us that science is not a cold pursuit of facts, but a celebration of mystery. He didn't reduce the universe to equations. He expanded it through understanding. His work invites us to see that uncertainty isn't the enemy of knowledge. It's its foundation. To know something truly is to stand in awe of how much more there is to learn. In the end, Feynman's vision changes the way we see reality itself. The world is not a rigid structure obeying fixed laws. It is a shimmering, self-interfering web of possibilities, each moment born from all that could have been. We are part of that web, made of it, moving through it, shaping it. The more we understand the universe, the more we realize that it is not something apart from us. It is us, thinking, questioning, wondering about itself. Reality, seen through Feynman's eyes, is not a finished truth, but an unfinished poem, one the universe has been writing since the beginning of time, and one we continue to help write every time we choose to look. Feynman's journey from a curious young physicist to one of the most brilliant minds in science was never about prestige or proving others wrong. It was about the pursuit of truth, truth that often looked stranger than imagination, yet always matched the quiet logic of the universe itself. His work revealed that reality is not the simple, mechanical world we once thought it was. It is a fluid, interconnected web where every possibility plays a role in shaping what we finally see.